spaces and symmetrisation of what equations.
Is there a...
This is the point.
Okay, how do we work? Thank you.
Okay.
Thank you, Yamo. And I'd like to say I'm very grateful to the organisers for the opportunity to speak here. So my talk will be about Fano 3 space and symmetrisation of quad equations. So this talk is about polynomials, actually. One polynomial in particular, which I'll give this Gothic F notation to. So this is a polynomial depending on 7 variables. And it has, it's not fully symmetric between all of them, but it has the symmetry of the Fano plane. So this is the Fano picture illustration of the Fano plane. These are permutations which generate the group of symmetries of this plane. So you can see that there's a W, X, Y, and a Z, and then somewhere else in the alphabet there's a P, Q, and R. So the W, X, Y, Z are supposed to be the familiar things, the quad, the quad, and the P, Q, and R. Well, P and Q are going to be like lattice parameters, and R is also lattice parameter-like. So we think about quad equations, and this talk is about generalization of quad equations. But in particular, the polynomials that define the quad equations. I'll come to the lattices later on. So just as a beginning point, this Fano plane, it seems relevant actually to talk about where it comes from. So Fano space was discovered by Gino Fano in 1892, and he was trying to obtain axioms for projective geometry. He obtained a list of 35 axioms, so they're not written here. I've written the 3 which were found by Veblen Young in 1908. So this is the good axiomatic system for projective geometry. But this is also a useful point to start to explain Fano's discovery. So 2 points determine a line. So first of all, what is projective geometry? It's a set of points and a set of lines where a line is a subset of points. The axiom is that any 2 points determine a line, so if there are 2 points, there exists exactly one line which contains the 2 points. The second axiom is a non-degeneracy condition, saying there must be at least 3 points on each line. And then this is the main axiom, this third one. So here, this notation. So here I've drawn 4 points. Wx denotes the line, which is determined according to axiom 1 by points W and X. So there is a line through W and X, and also through Y and Z. And the third axiom relates to the case when these 2 lines intersect at another point that's in the space. And it says that if we join WY and XZ, then they also intersect in a point. And so, of course, by symmetry, one can also imply that if this is a projective space, then there's another point of intersection here. So these original 4 points are in a special configuration, which we would call coplanar, and there are 3 diagonal points associated with them. So the case of the Fano plane is just the case when these 3 diagonal points are themselves collinear, which is a non-generic situation. So that corresponds to, in the associated vector space, that corresponds to characteristic 2, and it was convenient from Fano's axiomatic system to exclude this case. So he actually excluded it, but made a detailed footnote describing this space and also its high dimensional analogues. So this is the 3-dimensional version of the Fano plane, which is Fano 3 space, or it's also PG3-2 if you're familiar with that notation. The field is characteristic 2 and the dimension is 3 here, and this is projective geometry. So it's a finite projective geometry, finite projective space, three-dimensional. It contains 15 points and 15 lines, and 15 planes. And I found this on the internet. So this guy who's made this model, David Richer, and his homepage is here. He's also made several other models of geometric figures. So here you can see there are many. So there are 15 planes here. They're not all so obvious, but of course the 4 on the edge outside of the tetrahedron are. And you can also see, if you include the point at the center and the top part, everything excluding the bottom plane, you can see a cube. So there are faces of the cube, which themselves have diagonal lines through them. And there are 6 faces of a cube. So this is the cube so the point about this polynomial f, which I shall describe, is that it's consistent in Fano 3 space. And this is a generalization of consistency on the cube of quad equations. And the statement is that we impose the vanishing of the polynomial on each of the 15 planes. So that's 15 equations. And there are 15 points, and each point corresponds to a variable. So there are 15 variables, 15 equations. And there turn out to be 9 degrees of freedom, which is 9 more than you would expect. So there's a consistency property for this polynomial. So I've listed down the bottom 4 conjugacy classes of initial value problems. So this is not very useful information. It's only really useful to know that you can choose these 9 points freely, except that no 7 of them can be on the same plane. It turns out there are 4 cases which are different up to the automorphism group of the space. So the polynomial is actually quadratic in all the variables. So it's a generalization also of the ones that Maciek introduced previously. So there's a question about multivaluedness. If you give some set of 9 initial data, how many solutions are there for the rest of the data? And it does depend on the initial value that you choose, on where you put the initial values. The number of solutions can be either 32 or 16, depending where they are. So there is some notation going on here, which is a bit confusing to start with. But if you look at the center plane, it's all depending on p, and p has a subscript. So there's a natural notation here: 1, 2, 3, 1, 2, 2, 3, 3, 1, and 1, 2, 3, and then there's another variable v. So there are 7 p variables and 8 v variables, all with subindices. So the point about the v variables is that they correspond to the points of the cube, and the 7 p variables, they lie on the bottom. They lie on the bottom of this figure, and generalize the parameters. Okay. So the construction of this polynomial generalizes the one which Maciek showed previously, which we used to construct the multi-quadratic quad equations. So the procedure we had then was to start with the quad equations. So there's a natural symmetry. One can assume that you have a polynomial of 4 variables, w, x, y, z, which just has the symmetry of the quad like this. So that's the permutations which generate this symmetry group. But this is just order 8 symmetry group. This is the discriminant factorization property. So not 3 but 4 actually factors, because the parameters also sit in there. But w, x, and y, and z. So this is the discriminant of this polynomial as a quadratic polynomial in z. And these 2 conditions, 1 and 2, are sufficient to determine f uniquely up to an overall constant. Yeah. Okay. So what's the h? That's the key thing. So this is a polynomial which is quadratic in each of 7 variables. H is a polynomial which is quadratic in each of 3 variables, and h has an origin. Here's an explicit formula for h. So we don't need to construct h. We have a formula for it. It can be expressed conveniently as a discriminant itself. So here t is a dummy variable appearing in this expression, and we take the discriminant with respect to t. So this is actually quadratic in t, even though r is a cubic polynomial. No. Field of characteristic 2 is only in the sense of vector space associated to the projective space, which was the domain. The fields are just complex numbers. Yeah. So yeah, this is a quadratic expression in T, and if you take its discriminant, you get a function, a polynomial in 3 variables, which is symmetric in those 3 variables, which you can see by construction, which has the interpretation of the addition formula for a function f. So in particular, this holds. So there exists a function f for which this is true. And the way that f is constructed from this data, r and e naught. So e naught is a free constant that's not a root of r. So f is given as the analytic function, or meromorphic function, which is the solution of this initial value problem. So the point is that e naught, which is a complex constant, and r, which is a polynomial, cubic polynomial, or polynomial of degree at most 3, determine h and f. H is this triquadratic polynomial, which is this additional formula for the function f. So rather than taking the generic case, which we could, it's usual, it's conventional to take canonical forms because the calculations become simpler. And there will be 3 canonical forms, and this corresponds to the number of distinct roots of polynomial r. So in the case when r has 1 triple root, we'll put it at infinity, so r is just constant, non-zero constant. The corresponding function f is just f of alpha is alpha squared, and this is how the triquadratic polynomial looks, and this is how polynomial f looks. So given this data, all of these are determined uniquely. So this is the polynomial in 7 variables, the one that I started with. Here you can't see the symmetry, and I don't think there's an easy way to write down this polynomial where you can see the whole symmetry group. But you can see a subgroup of the symmetry group. You can see that I've treated P, Q, and R when writing this down differently than W, X, Y, and Z, so they kind of sit next to each other. Okay, so then there are 2 other canonical forms. One which is E naught equal to 1, and R of X to have 1 double root at infinity. The associated function f is cosh. This is what h looks like, and this is what f looks like. So this is a similar thing, quadratic in 7 variables. And finally, the elliptic case. So now there needs to be a free constant. So we take e naught to be that constant. E naught plays the role of the identity on the curve. Here the polynomial r has 3 distinct roots at minus c, 1 over c, and minus 1 over c. This is the associated elliptic function, which involves this constant cn over dn, where cn and dn are the Jacobi elliptic functions, with modulus k, which depends on this c. This is what h looks like, and this is what f looks like.
Sorry, James, can you remind me what h was again? What's the role of h?
This h?
Yeah.
So h is So h has an explicit formula in terms of r and e naught, so you can just compute. But the characterization of h is as the addition formula for this function f, defined by this ODE. So f of 0 is equal to e naught, so this is the value at the origin. And you see the differential equation involves this cubic polynomial r.
Also h arises from the factorization of the discriminant of the frac f, previous slide.
So f is then constructed in terms of h through this formula, exactly. Yeah. So once you've got h, you obtain f uniquely. So that's the thing. Why that should be true, it just turns out to be the case. That's unique. Okay, so the main thing about these polynomials is that they can contain as subcases the familiar quad equations. So the multi-quadratic case is more or less by construction because of what Maciek said in the introduction. Basically, we use the same discriminant factorization hypothesis. However, instead of r being free, r is chosen to be the identity point on the curve. And this makes these 2 other biquadratic, triquadratic polynomials degenerate. The ones that involve r, they just degenerate and are squares of multi-affine ones. So in this way, we recover some polynomial which I'll denote Q star, which depends on W, X, Y, and Z, and which is quadratic in those variables. And that's the familiar multi-quadratic quad equation, and P and Q have the interpretation of lattice parameters, and one has the multidimensional consistency. In the multi-affine case, it involves this H again. So if we impose that the three, let's say, parameters of the model are constrained so that they are related by the curve, then this F becomes, its discriminant vanishes, right? Because the way that we constructed it, H appeared in the discriminant with respect to Z. And due to the symmetry we imposed, the discriminant is 0 with respect to all of W, X, Y, and Z. So actually, this F in this case, when you make this assumption, this becomes the square of a multi-affine polynomial in W, X, Y, and Z. So we can solve this equation, H, P, Q, R equal to 0, without loss of generality. This is its solution, parameterized in terms of new parameters alpha and beta. So we use the function f and the fact that this is the addition law to parameterize the polynomial. When we do that, it becomes the square of a multi-affine polynomial. And this eta and this mu can in principle depend on alpha, beta, and p and q. Okay, so in particular, so these are the two reductions again. So on the Fano plane, one corresponds to taking one variable at one point and choosing its special value E0, and the other corresponds to taking one line, PQR, the circle line on the initial diagram, and imposing vanishing of H on that line. And then we get, in the rational case, this multi-quadratic model Q2 star and multi-affine model Q2. So they sit together in this larger polynomial. And here the constants which appear in these formulae are just equal to 1. So, and a similar thing happens in the trigonometric case. One obtains Q3 star and Q3 with delta equal 1. And the same happens in the elliptic case. So this is Q4 and this is Q4 star. So in this case, these constant eta and mu are slightly more complicated. So that's the connection back to the quad equations on the level of the polynomial. So, yeah, so I mean, I guess the natural question, okay, so I will now explain the reduction from the consistency in Fano 3 space to the consistent systems on the cube that we're familiar with for the quad equations, because it has a nice interpretation in terms of this picture of the Fano 3 space. So this is a picture of Fano 3 space, and it's not ideal in the sense that it looks pretty complicated compared to the geometric figure, but here I can label the points more easily. So bear with me. This again is the same picture as I had before, and so these are where these parameters p live, and we've got variables v which are associated with the cube. So what we're going to do is take this center or this bottom plane and fix now 3 variables in the Fano 3 space, all to be equal to E0. And those 3 variables all live on the same line. So we just single out one line in Fano 3 space, and in the center plane, it's the line represented by a circle. So in particular, on this plane, the polynomial f depends on all 3 of these 3 points, and we're setting all of them equal to E0. So this is a singular reduction of this plane. Because this polynomial f now vanishes for all values of p1, p2, p3, and p1, 2, 3. So it's satisfied automatically. You can choose these to be whatever you like, by virtue of this choice of these 3 variables on one line. So in the multi-affine case, the reduction is similar. It involves the center plane again, but now it involves 4 lines. And in particular, the 4 lines that do not pass through P1, 2, 3. So that's the 3 lines around the outside and the circular line again. And we impose vanishing of H on all 4 of those lines. If we do that, then this f is satisfied by virtue of this constraint for all values of p123. So again, this is a singular reduction. This is satisfied for any choice of this variable. So again, you can use the function f to parameterize this sequence of vanishing of h's by doing each one individually. And if you do that, and you come back to the whole space, so there are two cases. There's the multi-quadratic and multi-affine. In the multi-quadratic, one obtains that this equation and the two above and below it are all satisfied identically because they all involve this line. Three planes intersect in, or what? Let's say there are 3 planes that contain any particular line. So the equation is satisfied on these. These 6 equations correspond to the 6 faces of the cube. So that's the familiar story. But there are 6 additional equations which are kind of hidden. And the point about these ones is that they involve p123. So there's one other new variable, and you can, if you give a solution of these equations of the multi-affine equation, multi-quadratic equation, then you have 6, and you've determined all of the variables. So you have 6 quadratic equations for p123, and the consistency property is that they are all the same quadratic equation. So they determine the same variable. So coming to the multi-affine case, there are 4 lines on which h vanishes. And again, those lines all appear on the 6 faces of the cube. So these equations are all multi-affine, and these are the familiar quad equations around the cube. In this case, these 2 are not satisfied automatically, but they're well known because these are the equations on the tetrahedra. So these are recovered already in this larger picture. And then there are 6 additional equations. And once again, this p123 is not involved in any of these other equations. So these six quadratic equations for p123 are all satisfied. Okay, so that's the facts, let's say. So what does it mean? So first of all, I would like to say that coming back to this H, and in particular, actually, this story of the reduction to multi-affine models, we're imposing H on a set of 6 variables, and actually they have the symmetry of the tetrahedron. So you can put the variables like this, and impose vanishing of H on each face of the tetrahedron, where the variable is associated with edges. And this fact is actually, let's say, an algebraic fact, because this equation, this equation defined by H, defines a 2-valued binary operation. So fixing x and y, one obtains z as a 2-valued function of x and y. And the non-trivial feature of H is that this binary operation is associative. So in particular, this H determines a 2-valued group, which is the usual group structure on the elliptic curve. So if you look at the addition formula in this way, its consistency property on the tetrahedron captures the group structure on the elliptic curve. These are really equivalent things. Consistency on the tetrahedron, associativity in the 2 group. So the intuition about the high order model, this Gothic F model, is that this consistency property in Fano 3 space is like an analog of the addition formula in 2 dimensions. So one of the questions raised by the observations I've described is that this connects now Q4 and Q4 star. So there's a kind of strange thing going on here because we know Q4 star is related to F1 Yang-Baxter map. In turn, this is related to the NQC equation by Papageorgiou and Tongas and Veselov. And NQC equation is not elliptic type equation, whereas Q4 is. So there's a kind of bridge between the elliptic and the non-elliptic kind of models. And in particular, for this multi-quadratic model, what you can see is that this reduction where I introduced P and Q, the lattice parameters, and put them in a subscript, was really the wrong thing to do, because if I set E0, if I fix one of the variables in the Fano plane, the symmetry of the remaining variables is the tetrahedron. It's not the quad. So really, this should be depending on all variables, and it's really an equation on the tetrahedron. And that turns out to be, so and on the level of the quad itself, the more symmetric version of the quad is the tetrahedron, and you can ask what's the more symmetric version of the lattice, the whole of, for the quad equations, if the hypercube is the natural domain, generalizing the quad graphs, planar quad graphs. And if you ask what is the more symmetric version of that lattice, which is natural with respect to the symmetry of the tetrahedron, then you obtain a lattice which is not BCN anymore, which doesn't have BCN symmetry anymore. So it's no longer the hypercube. It's a richer structure which has automorphism group defined, which is a Coxeter group, which is defined by this Dynkin diagram. So parameters on the same level as variables seems to imply that there's some larger lattice of which the quad lattice is a subcase. And of course, then the natural question is, for the full Fano model, what is the analog of this? But that's not known yet. So again, this story is about polynomials, which are local things, and the question is about what is the lattice. So I've run out of time, so I'll leave some conclusions there. Thank you.
Questions?
One comment concerning the Fano 3 space. Baxter, at the time when he studied the Zamolodchikov equations, he associated some geometric interpretation of the one side of the identity, which he called rhombic dodecahedron, and it is exactly the Fano 3 space with labels associated to several labels and one central variable.
So Fano 3 space with a broken symmetry by singling out one variable.
Oh, you adding the central variable, which you remarked that by adding one more vertex, you make 4 cubes on the vertex of the tetrahedron.
Is it easy to see from this picture?
Yeah, but yeah, it is here. It is, yeah. So by adding central point, this describes both sides of the tetrahedral identity of the Zamolodchikov equation, where the variables sit on white vertices.
Okay, thank you.
Any further comments or questions?
Is there any Fano 4 space?
Right. Yeah. So the natural hypothesis is once you're consistent in Fano 3 space, you might want to consider the extended lattice to be Fano n space, right? But it's inconsistent on PG4 too. It's inconsistent in Fano 3 space, 4 space. So this surprised me. So
You have to replace that with something else.
yes. So the conjecture is that this is something which is already infinite in the case n is equal to 4. So infinite lattice, but with some kind of affine Weyl group symmetry.
Okay, so let's thank our speaker.